Okay, so now that we've built up the machinery of vectors some more, we can use this to build towards doing coordinate transformations. Now this will come in handy, especially when we do rotations later on, but it'll show up in all sorts of other places because often it is more convenient to analyze a problem in a coordinate system other than the one suggested by the laboratory frame or something like that. So often we'll transform to a coordinate system that's more convenient to do the calculations in, and then transform back out. Okay, so let's think about how this is going to work in general. So let's say that my coordinate system here, x, y, z, we'll call that the unprimed coordinate system, or the unprimed frame. Now, we could choose to work instead in this primed coordinate system here that I'm drawing in red. This will be the x prime axis, the y prime axis, and the z prime axis. Now we're going to be interested in looking at some arbitrary vector A. And we'll be expressing this differently in the two coordinate systems. Now it's important to realize this is still the same vector. The laws of nature don't depend on the coordinate system that we choose to study things in. So this is still the same vector, just with a different representation. So I could choose to represent my vector A in the unprimed coordinate system as some x component I hat plus some y component j hat plus some z component k hat. And we would get those by projecting the vector against, say, the z-axis here, so that would be the z component, projecting it down to the y-axis. Oops, keep projecting down. Okay, we project into the xy plane, we project back to the y-axis, that would be my AY. Project back to the x-axis, that would be my, this would be my AY, and this would be my AX, like so. Okay, and for my unit vectors, this would be my I, this would be my J, and that would be my K hat right there. Okay, now if I wanted to express this in the primed system, I wouldn't do anything any different. Except I would be writing it as A, and then I would be taking the x prime component, and we would have a different unit vector in the primed system. Similarly for the y, and similarly for the z. So when we're working that through, we would again do the same kind of projections as before. We would project this up against the z-axis, making that z-prime axis, making that bit right there a z-prime. And then we would go ahead and project this down into the x prime y prime plane, project back like so, making this piece a y prime, project over like that, making that piece a x prime like so. And similarly, our unit vectors here, this would be my I hat prime, that would be my j hat prime, and this would be my k hat prime. Okay. So the clue that we can take from this for how to change representations is we could get the x-coordinate by dotting a with I hat. So this would give me ax I hat dot I hat, but I hat dot I hat is 1. So that's how we can do it. So similarly, if I wanted to get it in the primed coordinate system, my ax prime would be equal to a dotted with I hat prime. Okay, that's cool. But now let's think how that's going to work. If I know my a in the unprimed frame here, this is going to become ax I hat plus ay j hat plus az k hat dotted into I prime. Now remember, the dot product distributes over vector addition, so we'll take advantage of that and express it like so. ax times I dot I prime plus ay times j dot I prime plus az times k dot I prime. Okay, so this bit here where we're dotting the unit vectors in the different coordinate systems together, that gets called a coefficient of transformation. And we could do this game similarly for the y prime and the z prime components, but I'm not going to write it out. So if we think of doing things in matrices, we remember that one way we can represent a vector is as a column, so ax, ay, az, like so. So I can generalize this idea into a matrix multiplication, which is what we're going to do now. So to express a in the primed system, so ax prime, ay prime, az prime. Now this isn't a different a, it's the same a, just represented in a different coordinate system. I'll be putting over here a vector in the unprimed system, and then you should be able to convince yourself that I will need I dot I prime here, j dot I prime, k dot I prime, and then this will be I dot j prime, j dot j prime, and k dot j prime. And then finally, I dot k prime, j dot k prime, and k dot k prime. We'll times all of that by our column vector ax, ay, az without any primes. This matrix right here gets called a transformation matrix. Okay, and we can similarly construct the transformation we would need if we were going the other way. So I'll leave it as an exercise for you to convince yourself that if I knew it in the primed coordinate system, need to go to the unprimed. This would be I prime dot I, j prime dot I, k prime dot I prime dot j, j prime dot j, k prime dot j, I prime dot k, j prime dot k and k prime dot k. And then my column vector would be ax prime, ay prime, az prime, like so. Okay, and like you might guess, this gets cleverly called the inverse. Transformation matrix. Now, some useful things to note here. These two matrices are orthogonal. So remembering back to linear algebra, our transformation matrix is called R. And if it's orthogonal, that means that its transpose is equal to its inverse. So this means, for instance, that I can write my vector A, I can write that as R transpose times R, because that's just multiplying by the inverse, so that's the same times A. So that's the same thing. Okay, so R inverse times R times A, which is the same thing as the unit matrix times A, which just gives me A. All right. So we can take advantage of this, we'll see, to build up more complicated transformations. Usually we don't try to do this all in one go. You can see that this becomes kind of a mess. So instead, what we do is we try to do transformations about successive, by rotating about successive axes until we get to our new coordinate system out from the old. We'll be able to see later that there's a pretty ironclad way of doing this that involves at most 3 such rotations. So let me just step through a quick example of that. So let's say, for instance, our first step here, so this is my original unprimed frame, x, y, z. I'm going to try to work towards getting, well, so the first step here would be, say, rather than trying to do all the rotations in one go, we instead say we'll keep the z-axis the same for the moment, but now our new x and y axes, my x, y, and x prime and y prime, have been rotated some angle phi away from the original ones. Okay, this helps to break things into bite-sized pieces. So for instance, I can look here and observe that the piece I dot I prime, that'll also be equal to piece j dot j prime. In both cases, this is a measure of how parallel the two vectors are with respect to each other. And so they will both be equal to the cosine of phi. Now to get some of the other cross terms, to get I dot j prime. So I is the unit vector. Let me go ahead and draw in our unit vectors again here. So that's I and j, and this here is I prime, and that's j prime. Okay. So I get I dot j prime. If we take a look at this, the angle between the two is going to be 90 degrees plus phi. So this would be equal to the cosine of 90 degrees plus phi. And if we remember our trig identities really well, that's the same thing as minus the sine of phi. And by the same token, to get j hat dot I prime, well, here's my I prime, there's my j hat. Okay, so this whole angle here is 90. Then I'm taking out from it phi here. So this turns out to be the cosine of 90 minus phi, and that works out to just be plus the sine of phi. Another one that we can get right away is we observe that k hat and k hat prime point in the same direction. So that means that k dot k hat prime is just equal to 1 because they're parallel to each other and they're both unit vectors. And you should be able to convince yourself that all of the other dot products that we could possibly have in our transformation matrix, basically all the other ones involving k hat, either the k hat or the k hat prime, will be perpendicular to any of the i's and j's that we have, and so the dot product will be 0. So this gives us a transformation matrix, let's just call it R1 real quick here, of cosine phi, sine phi, 0. I'm just putting in the dot products where they go, minus sine phi, cosine phi, 0, 0, 0, 1. Okay, so now that we have all that, we can go ahead and take a look at our new primed coordinate system. So just following what we have from before. So here's my x prime, there's my y prime, there's my, oops, that's just a little overboard there. There's my z prime, like so. And now I'll choose to do a rotation about my y prime axis, and we'll rotate through some angle theta. So this will be my y double prime. So this will be my z double prime axis, and similarly that will become my x double prime. Oops, drew that badly. Nope, that's right. My x double prime axis, like so. And we'll say that this angle is theta. So we can play the same game we did before. So I'll let you convince yourself here that my I prime dot I double prime will be equal to my k prime dot k double prime will give me cosine theta. I prime dot k double prime will be the sine of theta. And lastly, I'll have a I double prime dot k prime that turns out to be minus the sine of theta. And then my j prime dot j double prime is unity. So that gives me a rotation matrix, we'll call that R2. That's equal to cosine theta 0 minus sine theta 0, 1, 0, sine theta 0, cosine theta. So to build up the combined transformation to go from my original representation of A all the way into the double primed representation, so this would be my AX double prime, AY double prime, AZ double prime would be equal to, we'll start over here with my AX, AY, AZ. Well, if I first apply R1 to it, that much right there is going to give me my ax prime, ay prime, az prime as an intermediate step. And then once I have that, I can go ahead and operate my R2 in front of it. So the combined transformation matrix that I'll have will be the product of the two rotation matrices. So my complete rotation matrix, let's call it R, is equal to R2, R1. So when you look at these operators, the way you should think about them is to look at them from right to left as the order of operation. So this means we first do the rotation with the R1 and then the R2 rotation. So first rotating about the z-axis, then rotating about the new y-axis. Anyway, that turns out to be equal to, and it's not pretty, but you can just go ahead and multiply the matrices together. Cosine theta, cosine phi, cos theta, sine phi, minus sine theta. Let's try to make that look a little better. There we go. Minus sine theta. Then here we'll have a minus sine phi, a cosine phi, a 0, sine theta, cos phi, sine theta, sine phi, cos theta. So it's easier to kind of break these into nice little bite-sized pieces and combine them together. So as a little exercise in how to do this, we could imagine that we do just exactly that collection of transformations. We'll take our vector A, that's 3i hat plus 4j hat plus 5k hat, and we will first rotate 60 degrees about the z-axis and then rotate 30 degrees about the new y-axis, about the y prime axis. So this is about z without any primes, and then this becomes about y prime. Okay. So just to flesh that out a bit, we would get, so this ax double prime, ay double prime, az double prime, that would be equal to, so we'll have a cos 30, cos 60, cos 30, sine 60, negative sine 30, oops, try that again. And this will be times ax, ay, az, like so. Then we'll have here negative sine 60, cos 60, 0, sine 30, cos 60, sine 30, sine 60, cos 30, like so. Alright, so now we got all that. We remember what those values are. So that will be, see, cos of 30 is root 3 over 2. Cos 60 is a half. Cos 30 root 3 over 2. Sine 60 root 3 over 2. Then we have negative 1/2. Similarly, negative root 3 over 2, 1/2, 0. Then we'll have a half times a half times root 3 over 2, and just root 3 over 2 itself. And our components are 3, 4, 5. Okay. So we can clean this up a little bit. These here can become 4s and stuff, so we can make it look a little prettier if we want. We got root 3 over 4, just a 3/4, a minus a half. Then we'll have negative 3 root 3 over 4. Okay, they're not all pretty. Or I'm sorry, let's try that again. A negative root 3 over 2, 1/2, 0, 1/4, root 3 over 4, root 3 over 2 times our 3, 4, 5. And when I grind it all out, you wind up getting 3 root 3 over 4 plus a half, 2 minus 3 root 3 over 2, and 3 root 3 over 4 plus 3/4. Okay.